And I wanted to remind everyone that we're on this alternating schedule again. So next week we'll be meeting on Thursday instead of Tuesday like this week. So today we have two talks from Dr. McNeil and Dr. Schultz. And just to make sure that we remain on time, I'm going to turn it over to Shamali to introduce Dr. McNeil.
Hi everyone, my name is Shamali and I'm a fourth year in the macromolecular engineering program at UM and co-president of our student PMSE chapter. Today I'll be introducing Dr. Anne McNeil, who is a collegiate professor of chemistry and macromolecular science and engineering at the University of Michigan, Ann Arbor. She obtained her bachelor's from the College of William and Mary and her PhD from Cornell University. Dr. McNeil then joined the Massachusetts Institute of Technology as a L'Oreal postdoctoral fellow. In recent years, she has received many awards, including the Harold R. Johnson Diversity Service Award, the Claudia Joan Alexander Trailblazer Award, and the Faculty Recognition Award. She was also an AAAS Fellow in 2017 and a Guggenheim Fellow in 2019. Her talk today will be on developing synthetic approaches to more sustainable polymers. As a note, everyone should feel free to write questions in the chat throughout the talk, and then at the end of the talk, I'll relay them to Dr. McNeil to answer. Thank you.
Right. Thanks, Shamali, for the introduction, and thanks to all the students for the invitation to be a part of this summer symposium series. I think the COVID has changed the world a lot in many ways for the worse, but one of the ways I think it's changed our professional lives for the better is the ease in which we can do this type of communication that we used to do in person, sharing our research results. We can do it pretty easily on Zoom with the same kind of integrity and Q&A and back and forth discussion. So I'm super excited that the students have organized this awesome summer symposium series, and I'm even more excited to be a part of it. So thank you for that. And thank you for putting in all the time and effort. As Shamali mentioned, I'm going to talk about some of our work in the area of sustainable materials, and specifically I'm going to just talk about one of the projects in my lab. Normally I try to cram 2 projects into a talk, but I'm going to try to stay within my time frame. And actually let me start my timer too so I can keep an eye on the time. So I'm only going to tell you one story today, and then I'm going to do a little bit of discussion on some other initiatives that I've been working on as well. All right, so brief outline. I'm going to talk about science for about 30 minutes, and then I would like to spend a few minutes, hopefully about 5 minutes, telling you about Diversify Chemistry, an initiative I started that is aimed at helping to broaden the pool of diverse chemists out in academia and industry. And then I hope to reserve about 5 or 10 minutes, if we're lucky, for Q&A at the end to hear feedback from everyone that's listening. All right, so to get started, I want you to take a look at this picture. You've probably seen either this exact picture or something like this, or maybe you've actually seen this out in the environment, but there's no doubt that at this point in time, we have a huge plastic waste problem. It's been estimated that maybe close to 6.3 billion metric tons of plastic waste have been generated since the advent of the polymer industry. And approximately 80% of this waste is currently out in the environment, either in an uncontrolled fashion, as litter in the land or in the ocean, or it's in a controlled fashion in landfills. And overall, when I look at a picture like this and I see these numbers, it's actually very depressing. And when you think about it, I mean, we put so much energy and innovation and materials, resources into making these plastic bottles and these plastic products, that it's kind of a waste just to throw them out into even a controlled environment of a landfill. All of that innovation that went into these materials is just being wasted. So when I look at this as a polymer chemist, what I see is kind of like an Aldrich catalog. Why can't these plastic products be starting materials for something else? Why can't we keep the value that we've already invested into the material and maintain that value and give it a second life and a third life and a fourth life? And so that's what I'm going to talk to you about today. And one of the ways we're trying to look at waste plastic in a new way as a starting material for something else. But before I get there, I'm just going to give you a little bit more background about how we came to look at polymers this way and why we think this is the right way moving forward. And so I got to first talk about mechanical recycling a little bit. This has been around for probably about 40 or 50 years. And many of you are probably familiar with it. You know, there's curbside recycling of plastics. You can probably find a recycling bin at work as well. And basically the idea behind mechanical recycling is that we collect waste plastic when we're done using it, and then it gets sorted in a facility and then ground down into little pieces, hopefully mixed together with other pieces that are like it to make new products. But the myth of mechanical recycling is that this is a virtuous cycle and that it keeps on going. The reality is that it's actually kind of broken at this point. It doesn't keep the value of the material. We actually downgrade the quality of the plastic through the mechanical recycling process. And so it ends up being things like carpet fibers or park benches and things that we don't actually recycle after we're done using them. So overall, mechanical recycling produces lower quality materials with worse properties than the original material, which is why we can't go back and make another water bottle out of it. And there's many reasons why the properties go down. As you may be familiar, there's a lot of different additives in polymers, including like stabilizers and antioxidants and plasticizers. There's also a lot of colorants. And then, there isn't just one polyethylene out there. There's lots of polyethylenes. And even if you were just sticking to high density polyethylene, there's different molecular weights. So as you can imagine, you just get this like giant soup of different components, and it's just hard to regain any of the original pristine quality material properties after this process. In addition, mechanical recycling is limited because more complex materials, things that involve multiple plastic items, especially things that are like laminates where they're multi-layer films, they can't be easily mechanically recycled. And this only applies to a subset of plastics known as thermoplastics. And so for kind of all of these reasons, we're pretty bad at mechanical recycling. It's been estimated that only about 9% of our plastics are actually taken through this process of mechanical recycling. So this led my group and I to start thinking about this concept of, what would sustainability look like in the polymer field, and how can we, achieve that, and what can we do to try to get there? And I kind of put this as a little kind of tongue-in-cheek here of, can they save us? I'm just kind of referring to like, can they get rid of this plastic pollution problem? Like if there's value in these waste polymers, then we're less likely to just throw them out. And so like any card carrying chemist, we started with the IUPAC to try to find a definition. What is a sustainable polymer? I definitely had heard the term used many, many times over the last 20 years, but I didn't really know what it meant, like what criteria that we would use to define something as sustainable. So we went to IUPAC and there was no definition yet for a sustainable polymer. And so we decided to just search the literature and try to figure out, how are people using this term in the literature? So we looked through 10 different polymer-focused journals, 12 broad readership journals, and then the Web of Science. And we searched using these 4 different search criteria. And we ended up with over 6,000 papers, which we actually went through and read each one of them. And we kind of narrowed it down to what we call the most relevant group, which was about 646 papers. And by most relevant, I mean that there's at least a portion of the paper that is focused on the sustainability of the material that is being investigated. And so it's not just cited, but actually studied to a certain extent within the paper. And then we went through and read all 646 of these papers, actually multiple times by multiple co-authors on this review I'm going to talk about in a second. And so we read these very, very carefully, and we started coding them into different categories. And ultimately, we ended up with these 4 categories on the right, but at one point we had like 12 different categories that we were coding them into. And so the 4 categories I'm going to tell you about briefly are that the paper had a biomass-derived monomer, or maybe they used some principles of green chemistry in the synthesis of the material, or they looked at the end-of-life fate of the plastic or the polymer material that they were studying, or they performed, or even just cited, we give them credit if they just cited, a life cycle assessment or a techno-economic analysis. And some papers fit in multiple categories and some only fit in one, but we sorted them all out and then looked at what the data and the results said. And it was actually really fascinating. Fortunately, after doing all of this work, we got some really interesting conclusions. And one of the most interesting ones from my perspective is that over the last 20 years, the word sustainable has been most closely tied to a biomass-derived monomer. And so you can see in many years, it's actually the full set of papers from that year that use the word sustainable were all starting from a biomass-derived monomer. And over time, you can see that this is starting to separate. So the axis on the left is total number of papers, and for each year. that used one of those search terms in it, and the gray bar is the total, and then the red bar is what % of those had a biomass-derived monomer. So you can see over time this is changing more recently, but for many years it was the only thing that was synonymous with it. And this was a little bit surprising to us because if you look at the polymer market right now, just 1% of that polymer market is based on biomass-derived monomers. I know that this is changing over time, but it's a very small fraction, despite the sort of huge investment in it in the literature and the academics. And so the other thing that is a little surprising from this perspective is that depending on which source you use, but all sources agree that we are overusing our planet's biocapacity right now in other ways, you know, wood for construction and food, land for food and agriculture. So we're already overusing our planet's biocapacity. So the idea that we could switch maybe the other 99% of the polymer industry, these billions of metric tons of plastics, over to a biomass without sort of sacrificing something else is, I think, going to be problematic. So I'll show you on the next slide. We still view biomass as having an important role, but I don't think it is we don't think it is the end all be all for the future of sustainable polymers, that we have to have some other factors in there. And so for inspiration, we turn to this report from the Ellen MacArthur Foundation, which describes what they call a circular economy for plastics. And you can kind of see where it gets the name because you got some circles here. And the basic idea is that what we try to do is keep the value of the materials and the integrity of the materials through the entire process. So we make a product and then we use it. If it's possible, we're going to reuse as much as possible. And so that cycle is pretty obvious. You just keep reusing the plastic component. If you can't reuse it, then you want to put it through this other pathway that is what they call radically improved economics and quality of recycling. And so we're going to make the argument that this can't just be improvements in mechanical recycling, because we've been trying to make improvements in mechanical recycling for decades and we're not getting there. So some new form of recycling is needed. And of course, there's going to be some losses to other material streams. Things are going to end up in waste. And there's going to be some applications of polymers, like in farming and fishing, where we want the materials to break down at the end of their useful lifetime. And so we are going to have to supplement this circular economy with some renewably sourced feedstock. So this is where that biomass-derived monomers take place. But really, we think the focus right now for chemists should be on developing these new radically improved recycling methods. And so in this paper that we put together, we put forward really two ideas of where chemists can make a contribution to this. And so this is an area that is known as chemical recycling. And very briefly, that just means using chemistry to do a recycling process. And there's really two main categories. There's some other categories, but two really big categories. The first one is recycling via the monomer. And this one's kind of obvious. You take a polymer and you try to depolymerize it down to the monomer. And the reason that this is advantageous is that you can then purify that small molecule monomer and get it rid of those colorants and additives and stabilizers and any molecular weight differences in your samples or dispersity differences, because you're going all the way back down to the monomer. You purify that and then you repolymerize it, and there's no doubt you'll have like a pristine quality material again at the end. So this maintains the value. Of course, you spend some energy to break down the polymer and some more energy to make it again, but it retains the value of the materials in the waste stream. And as you can see from our graph, this idea of recycling to monomer is picking up. There's more and more papers focused on it in the future. Another possibility is what we call recycling via another material. So this is using chemistry to do a transformation on the polymer to either create maybe oligomers or long chain molecules, or maybe still a polymer and just with some different functionalization on it. We also call this recycling via repurposing because it kind of, I think, captures the idea. You're repurposing it, but maybe not going back to the original component that you had in the beginning. And this is, as you can see, not much interest in it for a very long time. And then now it's starting to grow again as we get towards the end of this later decade. So both of these areas are growing, and we think they should continue to grow. And we invite many chemists to join in this fray because we feel like there is really no greater problem facing humanity from a polymer chemist perspective than coming up with a way of dealing with this plastic waste. All right, so I mentioned a couple times that we put this into an article, and so you can find this. It was published earlier this year in ACS Macro Letters, and it was part of their 100th anniversary of macromolecular science. They put together a bunch of beautiful viewpoints. I encourage you to take a look at them all. They are really fantastic viewpoints, and we had a blast putting this one together, which we call Redefining Sustainable Polymers, and that's the idea of just shifting away from thinking of it just as a biomass-derived monomer. And I had the pleasure of working with a number of great colleagues on this. First, I worked with Professor Yutan Getzler. For those of you who are grad students in the audience, Yutan and I were both grad students at Cornell and friends back then and have maintained our friendship. And we were really excited to work together in this professional context. I was aided by a very talented postdoc in the lab, Dr. Danielle Fagnani, who is a UF alum. So for the UF organizers, you can take a look at that. And graduate student Jessica Tammy, who's also a UF alum. And a postdoc in the UK, Dr. Graham Copley, and an undergrad at Michigan, Mackenzie Clemens. And we just had a great time putting this together, and we've been very excited about the interest from the community in this conversation. All right, so moving on to the science part, where I'm going to tell you a story specifically from our lab. Maybe not as a surprise, I'm going to tell you about some form of chemical recycling. And specifically, I'm going to tell you about this one on the lower right hand, this idea of taking a waste polymer and giving it a second life as another polymer material using some chemical transformations. And this work just appeared on Nature Communications, maybe earlier this month or at the end of last month. And the subject of the material that we're going to do the chemical recycling for are diapers, specifically the superabsorbent polymer inside the diaper. And for those of you who haven't either been around really young children or haven't done it in a long time, let me just calibrate you for a little bit. Children go through about 5,000 diapers in their pre-potty training lifetime, which is age 0 to about 2 years of age. 5,000 diapers from one kid. This corresponds to about 20 billion diapers being added to the landfill each year in the US alone, which corresponds to about 3.5 million tons of waste per year. And so this is a huge waste problem. They're not recycled at all. There are some versions that you can buy that you can wash, but it's a really small percent of the market, in part because of convenience of disposable diapers and also kind of a little bit of the grossness of having to sort of wash yourself the diaper and put it back on your kid. So we were interested in this problem in part because we were contacted by Procter & Gamble and asked to put in a proposal on the idea. And this is part of P&G's commitment to environmental sustainability for their company. They have these really ambitious goals, which they call Ambition 2030. And in terms of society, they view this waste, this diaper waste, as being a huge problem for society because we have to landfill it. It's not going anywhere else. And so in their goals for society, they want to say they advance these recycling solutions. And I really like this brochure is meant for the public, and it's probably also meant for their shareholders. But I love the fact that they define chemical recycling in the context of this, why we're focused on this. So they say this gives us an opportunity to recover worth from waste and create secondary raw materials for higher value applications. So that is the definition of like what chemical recycling is. And so I love that that's just kind of their selling point as well for why this is a good opportunity for them to invest in. And they hope to have 10 facilities operational by 2030, which is just a few years from now. So this is pretty exciting. And P&G is the leading manufacturer of diapers in the US. And so they were a perfect partner for this. And in case it's not clear already, they funded this work and funded my student. So I have to disclose that as well. Okay, so for those of you who've never taken apart a diaper before, you will find that it is a multi-layer material. It's got at least 4 different layers. There's a top and a bottom sheet that are both structural and for comfort of the child wearing them. These are typically made of polyethylene or polypropylene. And then on the inside, there's a mixture of 2 different materials, usually this acquisition layer, which is typically cellulose, and then the absorbent layer, which is this super absorbent polymer called sodium polyacrylate. And that's shown here in this like purplish color. These are actually really mixed together. They're not kind of separate layers usually. And this superabsorbent polymer has this general structure shown down here. It's a mostly linear polymer with a little bit of cross-linking that has a side chain salt-based group on there. And because of that and the cross-linking, it's kind of a gel-like material that really absorbs water to solvate these ions. And so it can absorb up to 30 grams of urine or up to 1,000 grams of water for every gram of the polymer. So it's a very absorbent material. And so what we said when we started this project was like, what can we make this polymer into? And I will be honest, we spent a couple of months first trying to go back to monomer, that recycling via monomer route, because that would be better, right? To make the monomer and then remake more diapers out of it. That's the ideal recycling. But this polymer was very resistant to depolymerization to form monomer. And I will leave it at that. If you want to know more, we can talk about that in the Q&A. And so instead we went with this recycling via repurposing, and there's a really obvious transformation here. We've got a acid functional group, and if we switch that to an ester, then we have a polyacrylate, which is used in a wide variety of applications like paints, coatings, and adhesives. We decided to target specifically adhesives because they have very simple acrylate structures. So with a single type of R group on here, we can make an adhesive. And specifically, we can make one of these pressure sensitive adhesives. So that's a very simple chemical transformation, one functional group to the other across the whole polymer. Unfortunately, the acronym or abbreviation here is unfortunate. So we go from an SAP, which is the Procter & Gamble speak for superabsorbent polymer, to the world's acronym for pressure sensitive adhesives, PSA. Because of this vegetable soup, I'm just going to avoid using those acronyms, but I just wanted you to know that they're out there. And the PSA market is about $13 billion. And it's growing every single year because there's more and more applications of these types of adhesives. All right, so to get from product A to product B, we had to do 3 different chemical synthetic steps. The first one, I mentioned that this superabsorbent polymer is lightly cross-linked. We had to get rid of those cross-links. That would break down the gel and make a soluble polymer. The next thing we thought we had to do was decrease the molar mass, because the properties of adhesives kind of maximize in the middle of a molecular weight plot. So if you get too high, the properties are not very good. And if you go too low, molecular weight, the properties aren't very good. You kind of got to be in this middle range. And so we thought we needed to lower the molecular weight because the superabsorbent polymer was very big. And then our last step, of course, is to change that acid functional group to the ester. And all of the work I'm going to talk to you about today was done by a single graduate student at my lab, Takunda Chazovachi, who just recently graduated a few weeks ago, and I think actually started at P&G on yesterday. So, or not P&G, PPG, speaking of acronym problems. Different company. This is the Pittsburgh Paint and Something company. They do more paints than the P&G, which is more consumer products. Okay, so the SAP, as I mentioned, the superabsorbent polymer, we're going to call this PAA PNG for polyacrylic acid from PNG. It has, fortunately, a very simple cross-linker. It's a diacrylate, so it was a bis ester with the 2 acrylate groups on there that they just co-polymerize in the polymerization. And so it's very easy to break this down. We can use either base or acid just to do a very simple ester hydrolysis. So Takunda spent quite a bit of time optimizing both of these procedures, looking at the quantities of materials he was using, the temperatures that he was using, and the time of the reaction. And I just want to point out that this was not an easy reaction to monitor. It's not like you can do this in the NMR tube or, some other sort of in situ analysis. And the reason is because when you add your reagents to the superabsorbent polymer, you just get it absorbed. So you end up with a swollen gel as your starting point. And then over time with heating and the reaction happening and breaking the cross-links, then it starts to dissolve in solution. So the only way Takunda could monitor what was happening in this reaction was to look at changes in viscosity. And because you can't really do that in situ, he basically had to set up individual reactions and stop them at different times and measure the viscosity on each of those reactions. So this was like an enormous amount of effort. And initially, we fell into this trap of thinking that this top route, this base catalyzed or base mediated route, was better because it used less reagent, it had lower temperatures and shorter times. But we were prompted to do a life cycle assessment, both from our own sort of realization that we need to start doing these more when we were writing that review, and prompted by some reviewers. And so when we performed the life cycle assessment in collaboration with some co-authors at Michigan, which I will show you later, what we found was pretty shocking. The sodium hydroxide pathway was like 10 times worse than the acid-mediated pathway, even though we use more acid, higher temperatures, and longer times. And it just goes down to the fact that sodium hydroxide is much more energy intensive to make than sulfuric acid. So it really has nothing to do with our reaction conditions and everything to do with the synthesis of sodium hydroxide versus sulfuric acid. And so I'm going to show a couple of these plots in my talk. So I just want to take a quick second to describe what they mean. So on the left here, CED is cumulative energy demand, and this is the megajoules of energy that go into the system to make 1 kilogram of polymer out. And so that's all the bars that are in black highlighted are cumulative energy demand. So you're comparing this bar to this bar. And then the gray outlined bars correspond to global warming potential. And this is the kilograms of CO2 that is released per kilogram of polymer made. And so again, you're comparing this gray bar to this gray bar. So you can see it's a factor of 10, whether you look at cumulative energy demand or the global warming potential, it's 10 times worse to use the base. Okay, so we're going to proceed then with this product from the acid catalyzed pathway for the decross-linking. And I just want to point out, because this is kind of important when you're talking about trying to do things on an industrial scale, is that we don't isolate the material after this step and we don't do any purification. We just take the reaction mixture after it cools down and take it directly into the next step. Okay, so the next step, as I mentioned, we wanted to decrease the molar mass of the polymer, and one of the best ways to do this sort of without destroying the integrity of the polymer is to use a process known as ultrasonication. This can and is done on an industrial scale, so that didn't really slow us down at all thinking about this. Obviously, this isn't the size of the instrument that they use on industrial scale, but it has been scaled up and there's manufacturers for the equipment to do this. And what happens in sonication is basically the probe tip vibrates at a really high frequency, and that generates these microscopic bubbles. These bubbles expand a little bit until they become unstable, and then they collapse. And during that rapid collapse, if your polymer chain is nearby, it gets like sucked in. And if the molecular weight is high enough such that you have some entanglements and it can't untangle fast enough, you basically just rip the chain apart. And this keeps happening until your chains are small enough that they can flow with the collapse of the bubble. So it's purely mechanically induced. And so as a result, we shouldn't see any change in the side chain chemistry. Our carboxylic acid groups should still be present. So this is, I'm going to show you on the left a quick video, what it looks like when you turn it on. You can see the microscopic bubbles kind of forming. We have a jacketed beaker here just to control the temperature because it tends to heat up if you don't have that there. And we sonicate at 20 kilohertz frequency for various time periods shown down here, and this is in minutes. And as you can see, the molecular weight changes substantially very early because you're breaking these really big chains into smaller chains. And then the sort of diminishing returns happens as you get to what's known as this limiting molecular weight. And so this is going to be different for every polymer, but it's basically the size in which there's no longer any entanglements so that you can't pull against anything and you don't get any more cleavage. For our purposes of the adhesive, we just wanted to be down here in this like 400 kilogram per mole area. So we just stopped it after about 1 minute. We didn't need that much sonication. And then we did some dialysis to remove the acid from that first step, and then lyophilization to generate a solid polymer that we could handle, measure the yield, and work with. And both of these steps are done on industrial scale. So those are fairly common purifications. And what we found is we got 91% yield for the 2 steps, the decross-linking plus the sonication. And we confirmed, to the extent that you can confirm by proton NMR spectroscopy, we see essentially no change in the ratio of the 2 peaks along the backbone, which supports the idea that we didn't lose much, if any, of the side chain groups on there through a decarboxylation. Okay, so now we're on our third and final step, and this is the esterification step. And I'll be honest again, here we spent many months doing other esterifications than the one I'm going to show you here, because we thought that this one was going to be inferior. So this is a typical Fischer esterification where you take your acid, you put it in the alcohol you're trying to form the ester of. In this case, it's 2-ethylhexanol, which is shown down here, this 2-ethylhexyl group. You throw in a little bit of acid as a catalyst, heat it up, and you should generate some of the ester and then water byproduct. And the reason we stayed away from this for a while is we were worried about the fact that this wouldn't go to conversion, because you have to work pretty hard to remove that water in order to push the reaction all the way over. And we wanted to push the reaction all the way over. So in industry, they actually use this technique to take the acrylic acid monomer and turn it into an acrylate monomer. So this is done on the small molecule a lot in industry, and they use, high vacuum or some sort of azeotropic distillation to remove the water. But we didn't want to do that at first, and so we avoided this. But then I'm going to tell you, we came back to this, and actually we should have just started here because it worked fantastically. For reasons we didn't fully understand when we first set up this reaction, we saw what was quantitative conversion. Again, this is using NMR spectroscopy, so you kind of have to take this with a grain of salt, because NMR spectroscopy is like, maybe 95% of what you can see. And also we're on a polymer, which adds complexity to the analysis from, slow diffusion and things like that, slow relaxation. So to the extent that we can trust the NMR spectroscopy to say that we're close to quantitative, it was close to quantitative with the conversion, and we did nothing to remove the water. So we didn't have any vacuum or azeotropic distillation. So this got us, of course, very interested, and we went down this rabbit hole to explore it some more. So I'm going to tell you about the rabbit hole and everything we learned. But before I get there, I just want to tell you that when we isolate this polymer via precipitation, we get about 81% yield of isolated material. And by NMR, the conversion to the ester is quantitative. All right, so the first thing we did, because we didn't really trust these results, is that we just added water to the reaction at the beginning. So we added an equal molar ratio of the alcohol of interest and water, and we still saw what looked like quantitative conversion to the ester, which was like really surprising. So we started to suspect that the 2-ethylhexanol was just too hydrophobic, and so it was excluding water from the reaction environment. But we also knew that our substrate was pretty hydrophobic. This polymer backbone is kind of hydrophobic, so maybe that was also helping exclude water from the reaction environment. So we switched to these small molecules so that we could first quantify with more precision using an internal standard what the conversion is, and because we could more easily test this idea of hydrophobicity. And so we took first at the top this acetic acid monomer or molecule and treated it with an alcohol and water, same conditions as I showed you on the bottom of the last slide, equal molar mixtures of those two. And what we saw when we used our 2-ethylhexanol is we saw, again, high conversion to the ester, whereas if we use something that water is more miscible in, like ethanol, we get the lower expected conversion when you have water present, so you don't go to full conversion to the ester. So what this tells us already is that our alcohol is pretty hydrophobic and playing a pretty significant role in pushing the reaction towards the conversion. But we did one more set of experiments. We looked at this undecanoic acid to look at the question of the hydrophobicity of the substrate. So using identical reaction conditions as above, what we saw was quantitative conversion using the more hydrophobic alcohol and an increase in the conversion when we use the ethanol. So we go from 67 to 83% conversion. So both sets of these experiments tell us that the hydrophobicity of the alcohol was really important to our high conversion, and the hydrophobicity of our substrate seems to also be playing a role in helping with that high conversion to the ester. So either way, I mean, we're obviously happy that it turned out this way, and it was really interesting to dig through this story, but it was not expected at all. Okay, so last but not least, I need to tell you about the rheological properties of these materials, and I see that I'm running up to my time, so I'm going to go through some of these last things a little bit more quickly so that we have some time to talk about other stuff. So we measure the properties of adhesives using a rheometer. This is not how the measurement is done. This is what it looks like when Takunda is trying to clean up after a measurement, but I really liked this picture because it kind of shows you the stickiness and cohesiveness of this adhesive. And the way people classify adhesives is using this concept known as Chain's viscoelastic window. There's actually like 5 windows here. And the idea is that you look at the elastic and storage modulus under different frequencies, these bounding frequencies, and then that gives you this like little square that you can determine where your adhesive fits. And so our system where we skipped the sonication step completely, so we just went from decross-linking to esterification. We landed in this central region adhesive, which is these general purpose adhesives, things like labels and stickers. And if we sonicate the material, depending on sort of the concentration of the polymer in solution, we get different molecular weights. But as we decrease the molecular weight of the material, we end up in this lower quadrant, quadrant 3, which corresponds to removable PSA. So these are ones that like stick together instead of to your surface. Post-it notes fit in this category as well. And so we can basically tune which type of PSA we get out of the system using the sonication to control the molecular weight. Okay, so this last slide, or second to last slide of the science part is kind of important because I want to show you how we took the extra step to do the comparison. So I know the chemistry was simple, you know, acid catalyzed decross-linking, sonication, and then acid catalyzed esterification. Some of these reactions are known for, you know, hundreds of years. But when we put it all together, it puts a pretty compelling story for chemical recycling. So on the left here, I'm going to compare, and we're going to do the life cycle analysis on the next slide, but we're going to compare the approach starting from petroleum, going through extraction, cracking, and oxidation to make the acrylic acid, do the esterification to make the acrylate, and then do the polymerization to make our adhesive. And so the adhesive here in the central section is this poly-2-ethylhexyl acrylate that we targeted. So we looked at the synthesis from industry of that polymer, and then the synthesis from the diaper. And this is a picture of my daughter with a dirty diaper on her. And what I want to mention, and I haven't mentioned yet, is that there's a company that P&G owns called PhotoSmart, which has a patented process for sterilizing, number one, and then separating the components of diapers. And so we included all of the energy and processes of the PhotoSmart process because the life cycle analysis for that has been reported. So we basically are starting our life cycle assessment from this dirty diaper through the isolation, separation of the materials, then our chemical steps of decross-linking, maybe sonication, and then esterification to generate our same PSA. So this work was done, this later work was done in collaboration with Professor Jose Alfaro from the School for Environment and Sustainability and their student Madeline Summers. And so this is the same plot I was showing you before with cumulative energy demand on the left in the black bars, and then global warming potential on the right in gray bars. And then across the bottom here are the different routes. So first on the left, the industrial route shown in kind of the light gray, you'll notice is bigger. So it requires more energy and releases more CO2 than any of the routes that we developed. And the best route in our case is the one where there's no sonication, which is not a surprise, right? There's less energy because you're not using the sonicator. And if you compare our no sonication route to the industrial route, we see a 25% reduction in energy and a 22% reduction in global warming potential. And so this was a really satisfying sort of conclusion to this work. And I call it a conclusion because it came late in the stage of putting together this work. But we put in the review or viewpoint that we put together, and I firmly believe that we polymer scientists need to be doing or collaborating with people to do these types of analyses while we're developing the chemistry. And that's actually leading me to this slide. I normally don't put this up in seminars, but since I'm talking to mostly students and graduate students, I want to just normalize rejection and everything. So this paper was originally submitted first to JAX, then Nature Chemistry, and was doubly rejected without review. Submitted to Nature Communications a year ago, rejected after getting 1 negative review and 2 positive reviews. Then we spent 8 months doing additional work, and that was adding the LCA, which told us that the sodium hydroxide was a bad starting point at the very beginning. So we switched to the acid catalyzed one and then had to redo all of the stuff afterwards. So all of the sonication experiments, all of the rheology experiments, everything was redone. So we basically redid the entire paper because we weren't looking at the LCA in the beginning. Submitted it to Nature Chemistry again, desk rejected without feedback, and then went back to Nature Communications with the response to reviewers from the previous one. Still had to do another round of revisions after that because we still had one doubting reviewer, and then was finally accepted and online. So this was a year-long process to try to get this published. And I mean, to the reviewers' credit, the paper did get a lot better. Forcing us to sort of like think and do this LCA was really fantastic. And I'm glad that we spent the time to do it. But rejection is still hard. It's hard on me still. It's hard on the student. I think as a community, I have a lot of things to say about this, but I think we need to do better than just rejecting without any feedback at all, because I don't think that helps move science forward. Okay, so I talked a lot about one project in my group by a student who just graduated, but I still have a lot of other students in the lab who are working on a lot of projects. And so I have a bunch of people working on recycling via the monomer. We have also a group of people working on recycling via this repurposing. We also do work in redox flow batteries. We have a project in cleaning up microplastics out in the environment, and we still have some projects from earlier in my career on conjugated polymers. So if you're interested in any of these, you can take a look at my website to get some more details on these projects. All right, so I want to spend a few minutes. Let me see how much time I've used. Okay, I will spend 3 minutes going through diversified chemistry because I just want to take this opportunity so that you know that it exists and you can use it. And then I'll stop so you can do questions and answers. So diversifiedchemistry.com is the website. And when it first started, it was an academic website. So it was mostly professors, lecturers, teaching faculty, and postdocs. But thanks to generous funding from Merck earlier this year, we opened up 2 additional databases, one for grad students and postdocs, that's most of you who are listening, and also for industrial scientists. And the goal of this website is to make it easier to find people, mentors, people to hire, people to review papers, people to give talks, just easier to find people that come from diverse backgrounds. And so the idea is based on social science, where our brain is much better at reacting to information than it is recalling it from memory. And this is especially true when it comes to trying to come up with a list. So a list of speakers for a seminar series like the one I'm in now. If you start from a more diverse list, or if you start from any list really, you will end up with a more diverse group than if you just sit there and try to come up with names on the fly. And I'm sure all of you can recognize this because you've probably experienced it at some point, but there's a lot of social science research to back it up. All right, so I'm going to skip the industrial and I'm going to just jump to the grad student postdoc one. So this is a new database. We have 190 entries. I would love it if everybody on the call could just sign up and then get one more person to sign up because I want to get to about 500 by the end of the summer. And the idea for putting it on here is for other people to find you, right? So if you put your year of anticipated graduation, don't worry, we're not going to hold you to it. We're not going to check if you graduated on time. Just put your year of anticipated graduation and when you think you'll be on the job market, because recruiters are looking at this, you know, faculty who are searching for more faculty, industry who's searching for new employees. Everyone's going to look at this and look to see who they should contact and encourage to apply for their position. And then you get to also say what you're pursuing a career in. And you know, people haven't been filling this out, I think, because they're nervous. We're not going to hold you to it. It's just what you are and where you are right now. You'll also notice the self-identification side. There's I'm going to skip that. A legend, so you can pick one of these if you fall into this category of being underrepresented in chemistry. And then you also have the opportunity to add things that might be unique to your situation that that you want people to know about from on a public database. So and then I just want to mention real quick, I also run a Twitter feed for Diversify Chem where I try to highlight the people on the site. I've been variable at my activity level in this. It just depends on sort of time of year and busyness, but I do try to keep that fairly active. I will skip all of this and just end my talk by sharing this quote that I try to think about almost every day. And what happened, just the really short version of the story, is both my parents had passed away, and I went with my sister and brother to spread their ashes in this park that meant a lot to us growing up. And after we spread their ashes, I was just walking around being very reflective about like the purpose of life, why we're here, all of this stuff. And I saw this plaque on this bench that just really hit me. It's like, be happy for this moment because this moment is your life. I think especially in graduate school and college, we're always thinking about like, oh, I just need to do this for 3 years and then I'll go do this for 2 years and then I'll get this job or I'll get this, you know, high paying, whatever you want to do with your life. We're always thinking about this like next step, but in reality, like your life is going by. So make sure that you're doing things that keep you happy right now and don't wait for this like future thing. And this is what I constantly have to tell myself too. Don't think about this next grant, just be happy today for what today is. Okay, that's all. I want to just conclude by showing a picture of my group. I am very, very lucky to work with a large group of very talented students and postdocs, and I just enjoy, they make the job worth doing. And so I want to thank them for being who they are and thank all of our funding agencies. And thank you for your attention. I'm happy to answer any questions.
Thank you, Professor McNeil, for a really good talk. I really enjoyed your talk, but also that you talked about other things in the academic journey. We have quite a few questions in the chat. I'm not sure, would you prefer for me to relay them to you, or would you like to read them and answer them on your own?
I'm more than happy to read them out loud and then answer them. And I can just start from James at the top. Okay, what means of depolymerization did you attempt with the acrylate-based polymers? I actually have a slide for that because I couldn't bear to take it out of the talk. So let me see if I can advance to my next slide here. There we go. So do you foresee polymers without heteroatoms in the backbone readily undergoing depolymerization? Okay, that's the second part of the question. So the first question is, what did you try? So we did an extensive literature search first, and what you find is if you try to heat the crap out of these polymers, you just get decarboxylation or dehydration and formation of cyclic anhydrides. And so we knew that heating alone wasn't going to do it. One of my former colleagues actually just recently had a paper out where they used microwave heating and then the introduction of radicals to try to break down the backbone. And this worked to break down the backbone into oligomers, but they still got between 40 and 60% decarboxylation. And from my perspective, any decarboxylation or change in side chain chemistry is a reduction in the quality of the material. And so we don't want to do that. And so we were really intrigued by these previous reports by Haddleton and Zhu that had shown that under ATRP conditions, so while there was an active chain end, they saw spontaneous reversion to the monomer. And so we started there and we were like, let's try these out. And we tried to reproduce both of these chemistries, but found them to be not super reliable in our hands. And we tried contacting the authors and we're actually working with them over Zoom at one point to try to reproduce it, and we couldn't get it to work. And that was a problem. And then the other problem was that we don't really have an active chain end. You'd have to introduce one, you know, to get it to work. So we just decided this was a hill we were tired of trying to bark up, and we were going to just try the other route instead. And then the second question is, do you foresee polymers without heteroatoms in the backbone, like this one, where there's no heteroatoms, readily undergoing depolymerization? I think that's super challenging, but it's not impossible. Whether we say depolymerization all the way back to the monomer or depolymerization to something that could function as a monomer is like a different question. But if you want to just simply unzip to get back to this acrylate monomer, I think that's going to be really hard. And I'm not ruling out in the future because there's a lot of creative people out there thinking about this problem, but thermodynamically, it's very hard. Okay, just a reminder to post your questions in the chat. Okay. Next question, do you get the same conversion percentages of esterification even when you skip the sonication step? That is a great question. So if I can go back to, let me see if I can. Let me go back to the esterification. So one thing we tried is to take the reaction mixture after the decross linking. So just have that be the starting point, and then throw in, since water is not a problem, throw in the 2-ethylhexanol. There's already acid in there, so we don't need to add that, and then just heat it and do the esterification there. So it would essentially be a one pot, but two-step reaction. First, do the decross linking with water, add in the alcohol, and then do the one pot conversion. And it kind of worked, but didn't work great. Like the solution reaction turned black, and it didn't go well. And so we decided that we could basically just isolate the polymer. Instead of doing the sonication, we do the dialysis and the lyophilization from the sonication step. So we isolate the solid, pure, white crystalline polymer and then do the esterification. So when we do that, if we do the dialysis and lyophilization as a step in between decross linking and esterification, then we do get the same yields. But when we try to do it in one pot, we couldn't. Okay, I'm curious about how much energy is consumed in your open loop recycling. Okay, yeah, that I answered on that later slide. Adhesives often suffer from material creep over time. Did you do any creep studies on these? And if so, was there molecular weight dependence here as well? We did not dig into the adhesives much more than the rheology that I talked about. So we did not study creep, in part because we're starting to actually get some of these testers, that are typical for adhesives, like peel tack testing and stuff like that. but we didn't have any of that in our lab at the time. And so we didn't know what we were doing. We thought this was good enough. And I think it is good enough for sort of this thing. But now that we're actually using these adhesives in other applications and we're trying to push that science further, we are starting to measure these more advanced adhesive properties to better understand the quality of the materials. And I don't have any creep studies yet, but that's definitely on our radar for things that we need to look at in the future. And there should be a molecular weight dependence on it. Yeah. And I think that's all the questions.
Yeah, perfect. We're bumping right up towards the end of the time anyway. So
perfect. Well, thank you for the questions. Yeah.
Yeah. Everyone, if we could give a round of applause again for Dr. McNeil, that was an excellent talk. I'm going to make sure to share the Diversify Chem with the rest of my lab later today after the talk. So
thank you.
Yeah. So I would like to turn it over to Rachel now to introduce Dr. Schultz.
I can't get my video up, but that's okay because you don't need to see me. But thank you, James. Good morning, everyone. And like James said, my name is Rachel Bianculi, and I'm the incoming Vice President of the Poly PMSE chapter here at Virginia Tech. And it's with great pleasure that I get to introduce our second speaker today, Dr. Michael Schultz. Dr. Schultz received his bachelor's in chemistry at Iowa State University and went on to pursue his PhD in organic and polymer chemistry and a master's in pharmaceutical science under the direction of Ken Wagner at the University of Florida. Upon graduating, he worked with Professor Klaus Mullen at the Max Planck Institute for Polymer Research in Germany as a Fulbright Scholar, and then later went on to work with Professor Robert Grubbs at Caltech as a postdoctoral scholar. For the past 5 years, Dr. Schultz has been at Virginia Tech as an assistant professor in the chemistry department, and his research interests span both fundamental and applied polymer chemistry, including antiviral polymers, metal chelating materials, and polymer sequestriants. So with that, Dr. Schultz, the floor is yours.
All right. Thank you, Rachel, very much for the introduction, and thank you, everyone, for attending my talk today. I'm excited to follow such a fabulous talk already. I'll make one clarification to the introduction. I am currently describing myself as a rising fifth-year assistant professor here in the Department of Chemistry. Today is actually the fourth anniversary of starting as a professor here at Virginia Tech. So it's a particularly nice time, I think, to give a talk about what we've been up to in the last few years. So I view polymer chemistry as this collection of tools to make interesting materials that can be used to address fundamental challenges in our society. So in that sense, I'm very inspired by the end use or the unmet materials challenges that exist. And so then based on this philosophy, a number of projects have evolved in our group, but a lot of them tie back to this central idea of there are problems in the world, and a lot of these problems are amenable to a solution that's perhaps based on a new material or a material that's capable of a new function. So it's sometimes difficult to categorize all of these under one umbrella, and I've given up trying to a large degree. But a lot of them fall under a category that I'm calling polymer sequestrants. And essentially what I mean by that is this. So here I have my schematic representation of a polymer. And you could imagine this material having pendant groups that could perhaps bind to some target. What that target is could be many different things. In our group specifically, we're working on developing materials that can bind to or capture metals or toxins or drugs or viruses. Typically, I advise my students that the key to a good talk is only telling one story, and then I blatantly disregard my own advice when I'm asked to give presentations myself. So the solution to that conundrum that I've come up with is I'm going to spend the bulk of the time talking about just one of these topics, even though each of them could be a seminar in itself. And then I'll give kind of the 2-minute version of the other three, mostly focused on laying out the problem, because sometimes I think defining the problem is the most interesting part of a research project, perhaps second only to finding a solution. So for the next 35, 40 minutes or so, I want to talk about our efforts in studying metal chelating materials, specifically geared toward developing materials that could be used in metal extraction and separations applications. The specific metals that we're interested in are known as the rare earth elements. And so this is a group of elements, mostly in the F block of the periodic table, the lanthanide, so lanthanum through lutetium, plus yttrium and scandium. And the reason these metals are so interesting is because they're actually foundational in many ways to our modern society, in that they underpin many of the technologies that we've come to rely on. So, for example, hard drives, catalysts, magnets, including many clean energy technologies, actually depend to a great extent on having a reliable supply of these rare earth elements. So recognizing their importance to clean energy and other technologies, the Department of Energy a few years ago released this report where they analyzed the importance of various metals to clean energy technologies and plotted it against their supply risk. And interestingly, a lot of these rare earth elements, neodymium, dysprosium, et cetera, fall into this upper right-hand quadrant where they're critical to technology, but the supply risk is also very high. Interestingly, Virginia Tech happens to be kind of on the edge of one of the largest rare earth element deposits in the United States. And so we thought that our location was particularly appropriate for studying methods of developing rare earth element domestic production. So there are a few ways that this broad challenge intersects with polymer chemistry. And to really understand them, I want to talk briefly about how rare earth elements are currently extracted and separated. And by far the most common industrial method of accomplishing this task is a liquid-liquid extraction process. So in this approach, the rare earth elements are in aqueous solution, and then a chelating ligand is in an organic solution. And you have these large, essentially solvent extraction setups where over and over the metals are extracted from the aqueous into the organic layer, and the process is repeated. And by doing this 1,000 times or so, you can take advantage of very small separation factors to the extent that you can separate individual elements from each other. However, as you might imagine, these processes generate a large amount of chemical waste, which is clearly not ideal. And so alternative approaches are of great interest. And one of these alternative approaches is using a solid phase extraction approach. So in these technologies, there's some kind of polymer resin or a surface functionalized silica, for example, with chelating groups that can bind to the elements of interest. So you would flow a rare earth element containing solution through this bed of resin and then capture any individual elements. Then you might flow through an acidic solution to desorb the targeted elements from the resin and recover the metals of interest. A third approach to this challenge is something called polymer enhanced ultrafiltration. And the idea here is that in a typical filtration membrane, the pore size is tuned so that you reject entities of a certain size. However, a lot of metal ions of interest are very small, and so will often go through these pores. So one extraction approach is to add a chelating polymer to your solution that will bind to all of these metals and thereby increase the size of the overall entity that you're filtering out. So because the polymer metal conjugate is much larger than the metal ion itself, you can use a ultrafiltration membrane with a higher flux due to larger pores, because you can still reject the polymer metal conjugate. So each of these approaches could be enhanced by developing chelating polymers that can very selectively bind to specific elements. So our fundamental question is, how can we tune the polymer structure to vary this interaction? And like many things in chemistry, this is all going to come down to the thermodynamics of the interaction, or the thermodynamics of the metal ion binding to the polymer in solution. And so as a result of being interested in the underlying thermodynamics, we've spent a fair amount of time developing expertise in isothermal titration calorimetry, or ITC. So the way this experiment essentially works is you have an instrument with a reference cell containing solvent or buffer and a sample cell containing a polymer solution. Now into the sample cell, you titrate a metal ion containing solution, and the metal ion then binds to the polymer, and that interaction either absorbs or releases heat depending on if it's exothermic or endothermic. And then the machine can detect the temperature difference between these two cells. And so when you run this experiment, you generate a thermogram that looks like this, where each one of these spikes corresponds to an injection of a little bit of that metal ion containing solution. So when at the early points in this experiment, there are many binding sites available. And so you see these large changes in the heat. However, as the experiment progresses, fewer and fewer binding sites are available. And as a result, the change in heat becomes smaller until it reaches a plateau. Now you can integrate this data to generate an ITC curve. And this curve can actually tell you all of the thermodynamic parameters of the interaction. So the difference between that starting and ending plateau corresponds to the enthalpy. The slope of the line at the inflection point corresponds to the equilibrium constant for the interaction, the Ka. That inflection point also tells you the stoichiometry of the interaction. And so between those parameters, you can now generate, or you can now calculate your Gibbs free energy, and then the T delta S term using these equations that I'm sure we all have seen in general chemistry. So we've done these experiments on a number of different polymers. And here I'll show you some data from polyacrylic acid chelating to europium. And so what you, or chelating to 4 different rare earth elements. So what you see is that across this series from lanthanum to lutetium, the delta G value is about consistent across these 4 elements. But what's interesting is that this binding interaction is being driven entirely by the entropy. So these are unfavorable enthalpically. It's the very favorable entropy that gives you this negative or favorable delta G. And initially this may be counterintuitive, because if you imagine a polymer chain binding to a metal ion, you have 2 things that come together to make one thing that looks like it should be a decrease in entropy, because you're also losing degrees of conformational flexibility with regard to the polymer chain on top of it. The flaw with this picture, however, is that these interactions are occurring in solution. And so what's really happening is you have a polymer surrounded by solvent, water, you have a metal ion surrounded by water, and now these 2 are coordinating, and there's a release of water around the polymer and around the metal ion itself, and some changes in the hydration of both entities. And so these changes in the hydration are responsible then for this entropy-driven binding that we see consistently across this series of rare earth elements. Now, interestingly, nature seems to be well aware that these changes in solvation are very key to metal chelation or binding in general. So for example, a number of different proteins that are very selective for metal binding use relatively simple chelating ligands. So for example, lammodulin has this series of, or this region of carboxylic acid rich amino acid residues that is responsible for binding to rare earth elements. And it actually achieves about a 10 to the 8th fold selectivity for rare earth elements over calcium. This selectivity, however, is not due necessarily to the ligands themselves, but rather to specific conformational changes that happen upon metal binding. To give another example, carbonic anhydrase binds to zinc with strong preference for that metal over similar metals. And that particular interaction is mediated by optimizing the desolvation. And so I quote from this particular biochemistry paper from 20 years ago, that nature optimizes binding oftentimes by optimizing desolvation. And so thinking about how the polymer and the metal and the polymer metal complex are interacting with their solution, I think is key to developing new design parameters for optimizing or controlling this interaction between polymer and metal for metal extraction applications. So how can we start to think about these interactions, in particular looking at the changes in the solvation? And there's a very useful parameter that's been used for decades in biochemistry and physical chemistry in general, the heat capacity. Now, heat capacity relates to the other three thermodynamic parameters, enthalpy, entropy, Gibbs free energy, by this series of equations. And if you were to measure the change in the enthalpy as you change temperature, you can then use that data to generate the change in the heat capacity of the overall interaction. And in biochemistry, particularly in the protein literature, this has been leveraged to look at things like conformational rearrangements, changes in the solvent accessible surface area, the solvation of nonpolar versus polar moieties on a protein. And so we thought that perhaps measuring this parameter would allow us to start to interrogate the contributions of solvation to metal ion binding in polymers. So to look at this, we needed to synthesize a series of polymers that had a consistent chelating group, but a varied degree of hydrophobicity. And so to do that, we synthesized a modular polymer, which will allow us to create one parent material that can then be systematically derivatized, and thereby allowing us to hold consistent the degree of polymerization and the dispersity across a series of materials. Then we derivatized that material with a series of amino acids. Now this allowed us to install a consistent carboxylate group for chelating rare earth elements, but by varying the R group on the amino acid that we're appending to these polymers, we can systematically change the hydrophobicity from something that's relatively hydrophilic, like glycine, moving on through alanine or valine or leucine. Going further than this, in a series of more hydrophobic polymers proved a little problematic because we're bumping up against the solubility limits of the material in water at this point. But our hypothesis was that increasing this monomer hydrophobicity would increase the absolute value of the T delta S term. And the reason we thought this is that by increasing the hydrophobicity around the binding site, we thought that it would result in displacing more waters from the carboxylate and from the metal, which would then contribute to this entropy term that is driving all of these binding interactions. So to give you an idea of what this data looks like, here's a series of experiments where we're looking at the thermodynamics of binding between europium and this polyalanine acrylamide. And so you'll see as we increase the temperature from 5 degrees to 35 degrees C, the T delta S term, or the negative T delta S term decreases as we'd expect, we're changing the temperature, but also the enthalpy is increasing, which gives us a much smaller change in the delta G. And so this is an example of a phenomenon that's quite common in biochemistry and in other areas as well, known as enthalpy entropy compensation. Or another way to put it, no matter what you do, you can't make your binding interaction better, because if you improve your entropy, the enthalpy compensates. And that has been a challenge for many years. But if we were to plot those changes in the delta H against temperature, we now get this line. And the slope of this line then corresponds to our delta CP. It's a positive slope, and in biochemistry, this would typically be ascribed to hydration of hydrophobic surface area, or the exposure of non-polar surface area to solvent. We think that there's probably more going on here than that explanation, which I'll talk about in a second. So looking across this series of polymers that we've synthesized, we see that the delta G is actually about consistent among all of them. Interestingly, however, as you increase the hydrophobicity of these materials, you're increasing the delta CP quite significantly. It's almost an order of magnitude increase between the glycine and the leucine polymers. And this, I think, highlights the importance of probing a little bit deeper than just binding affinity or just the very basic thermodynamic parameters into these interactions. Because if you were to only look at delta G, for example, you wouldn't detect these subtle differences among these polymers. It's only at looking at these more involved, we'll say, thermodynamic parameters that these differences start to be revealed. So what's going on here? To explain it, I'd like to talk briefly about the structure of water. So say we have a glass of ice water and we were wondering what is the heat capacity of this water. When I was taking general chemistry, we all memorized that the heat capacity of water was 4.184 joules per grams degree Celsius, a number that has since proven an inconvenient number to remember, because what I really like to remember is the molar heat capacity of water for the purposes of these experiments. But it makes sense in the context of a Gen Chem class. Now, the liquid water, as we all know, has a higher density than ice. And this is because of the arrangement of those water molecules forming this hydrogen bonding network. The ice forms these crystal lattices, and there are different varieties of ice. But for our purposes in this talk, the important point is that these two populations of water have a different heat capacity. Ice water, frozen water, has a heat capacity of 37.6 joules per mole Kelvin. It's a lower entropy water. Bulk water, liquid water, has a heat capacity of 75.3. In our systems, we need to think about the different populations of water, because we have the bulk water, like typical liquid water, but we also have water that's being organized by the metal ion. So lanthanides are known as cosmotropes, meaning that they order the water even beyond their first hydration shell. And that water ordering, or that ordered water around the metal ions actually has a lower heat capacity than bulk water. Similarly, polar groups will order water and make and that ordered water around the polar groups has a lower heat capacity than bulk water. Hydrophobic groups, on the other hand, also order water, but that ordered water is actually a higher heat capacity water than bulk water. So it's a complex situation. So to help untangle some of these complexities, we are collaborating with one of my colleagues here at Virginia Tech, Professor Valerie Wellborn, who does atomistic simulations. And she modeled these polymer metal interactions in water for us so that we could start to try to convolute or deconvolute all of the processes that are occurring. And so there's lots of data in these simulations, and I'll show just one slide of it. So here we're looking at the radial distribution functions of the water around the carboxylates of the polymer. And this first peak at around 2 angstroms corresponds to that first hydration shell around the carboxylates. Then as you get further and further away from the carboxylates, these values approach 1, which corresponds to the ordering of bulk water. So this peak then corresponds to water that is ordered due to the presence of that carboxylate. The trend here is subtle, but it basically goes from leucine, valine, alanine, glycine. Interestingly though, when you add europium ions in the simulation, you see a much greater difference in this initial peak in the first hydration shell. Now we see that glycine is here on top, followed by valine and alanine about the same, and then a big drop to the leucine acrylamide. So what does this mean? What this is telling us is that in the simulations data, it's suggested that more waters are being displaced from the carboxylic acid upon metal binding for our most hydrophobic polymer. And interestingly, that simulations data corresponds reasonably well to some of our thermodynamics data measured by ITC, where we see that the largest increase in the entropy is actually on this most hydrophobic leucine polymer. I'll make one final comment on some of this data, and that's on the temperature dependence of the binding affinity. So here we're looking at the log Ka for the series at different temperatures. Now, what's fascinating about this data to me is that we have a very clear temperature trend for glycine and valine that completely reverses then for leucine. Alanine is kind of the mystery. It apparently does not care whatsoever at what temperature it is chelating metal ions, and for reasons that are currently unclear to me. But what this suggests is that there could be a mechanism for tuning the polymer structure such that you can control the binding affinity based on temperature. And this has implications then for thinking about how to recycle these materials. Because ideally, you would have some polymeric chelator that captures a metal of interest, but then you would want to decomplex that metal from the polymer so you can recover it. And what this data suggests is perhaps there's a way of doing that with temperature, likely with some other parameter, changing the pH, for example. But just by changing the environment around the chelation site, we can reverse this trend. And I think that opens up interesting and largely unexplored possibilities. So we've talked a lot about the role of water in these polymer metal interactions in aqueous solution. And to try to probe a little further into these interactions, we started thinking about solvent isotope effect studies. So we know water plays a critical role, and D2O forms stronger hydrogen bonds than H2O and has other subtle differences. So in theory, thermodynamic effects arising from solvent reorganization should produce solvent isotope effects. And so at the moment, we only have very preliminary data on these experiments, but I'll just show you a little bit. This is now looking at this polyglutamic acid chelating to europium-3 again. And when we're in H2O, a pH 4.9 acetate buffer, we once again see this entropy-driven binding interaction. But now when we switch over to D2O as our buffer, with PD 4.9 once again, we see this large decrease in the enthalpy. The delta G is about the same. What's interesting is now this delta H between H2O and D2O is about 6 kilojoules per mole, and we think can be directly related to the contribution of the hydrogen bonding in this interaction. Interestingly, once again, we see solvent isotope effects when it comes to the changes in heat capacity as well. And we think that this could be an approach to deconvoluting the changes in the hydration resulting from the interaction between metal and polymer in these experiments. So to briefly summarize some of our solution phase work, we've done a fair amount of experimenting on the thermodynamics of these metal ion polymer interactions in solution, looking at the effects of polymer hydrophobicity, starting to explore solvent isotope effects. And this work will directly apply to approaches like polymer enhanced ultrafiltration. But there's a large body of work surrounding alternative approaches to metal extraction, like solid phase materials. And we were also curious about that approach as well, particularly in the context of extracting rare earth elements from coal byproducts. So coal refuse from coal mining actually has a relatively high concentration of rare earth elements, in part because this layer right next to a coal seam is unusually high in rare earth elements. So when you mine the coal, all the rock that comes from either side of the coal seam also gets mined and usually discarded. But it's also an opportunity for taking materials that have already been mined and potentially extracting valuable materials from them. So then the typical process for extracting these is you have some feed preparation, rejecting the gangue elements, which are those unwanted metals in mining. And then that gets you about 90% of the rare earth oxide that can subsequently be separated. Now, in thinking about materials to chelate to rare earth elements, one functional group in particular is particularly attractive. That's the phosphonate group. It has a relatively high affinity for rare earth elements in particular. And so we spent some time synthesizing a polyethylene imine methylene phosphonate just because of its high degree of phosphonate functionalization along the polymer backbone. Branched PEIMP had been synthesized previously. We synthesized a linear version to try to reduce the complexity of the system. And once again, we did isothermal titration calorimetry to evaluate the thermodynamics. Again, we see that these are all being driven by the entropy. We tested a series of different molecular weights. We didn't detect any clear trends with regard to the molecular weight of the polymer on the binding thermodynamics to various rare earth elements. But what we were really thinking about in the end was, could we make analogous solid phase materials, so polymer resins, that would have this high degree of phosphonate functionalization? And so if you imagine designing this type of material, you could have a backbone structure similar to PEIMP, install these methylphosphonate groups and cross-link the whole thing with something like epichlorohydrin. And so we set about synthesizing this type of material, starting with diethylene triamine, cross-linked with epichlorohydrin to make this amine-containing resin, and then used Kabachnik Fields chemistry to install these methylphosphonate groups. This creates a solid chunk of material, which we can then grind up to make these fine particles of a polymer resin with high degrees of phosphonates. So then the basic experiment is, if we pack this material into a column and flow a solution of rare earth elements over it, can we capture them or even separate them using this particular material? So we investigated a number of different parameters within this experiment, starting with pH, which is certainly a key parameter. It was particularly important to evaluate pH in this context because of the number of different protonation states for we'll call it the repeat unit of this material. So you have two protons on a phosphonic acid group with different pKa's, plus the nitrogen, which can also be protonated. When working with rare earth elements in aqueous solution, typically the pH is kept on the acidic side because rare earth hydroxides will precipitate at basic pHs. And so what we found is we wanted to maximize the pH before the precipitation of the rare earth hydroxides in order to deprotonate the phosphonic acid group as much as possible. So we conducted these extraction experiments across the entire series of rare earth elements, and we observed this trend, or this general trend, where as the ionic radius decreases, the mole fraction of the rare earth element that gets absorbed increases. And so from this data, we can actually derive a distribution coefficient according to this equation, where V is the volume of solution, M is the mass of rare earth elements, and then the initial and final concentrations in the separation. And we see there's this clear relationship between the ionic radius and the percent capture, or the distribution coefficient. Now, what we really wanted to do was to see if we could correlate this kind of data with our solution measurements from ITC. And we found that the Ka measured by ITC correlated decently well with the Kd of the resin that we measured. And the reason that this would be particularly useful is because oftentimes when you develop a new solid phase extraction material, typically in order to evaluate it, you run these very long experiments to determine the resin capacity, to measure separation factors, often by essentially running a column, collecting fractions, and then running ICP-MS on every fraction. It's a very time-consuming process. But if you could use ITC to measure the thermodynamics of binding to a soluble analog of the resin and get data that could correlate to those resin experiments, then you could do in 2 hours what would typically take several days. And then we think that this approach would then accelerate testing of novel materials in these types of applications. The main outlier in this data is the lutetium, where in the resin, we captured a high mole fraction, whereas in the ITC data, it fell about in line with the rest of the rare earth elements. And we think that there's a kinetic effect going on here. So when we do a batch experiment to measure, to essentially measure the capacity of these resins, we take the resin, we put it in some container with a rare earth element solution, and then measure 3 days later how much of the rare earth element was captured by the resin and how much is still in solution. And when we measure the differences in the we'll call it the rare earth element capture of the resin in this batch experiment, we see that it's about the same across the board. There is no separation whatsoever, or no selectivity for one metal over the other. However, in the flow experiments, interestingly, now we start to see separation factors. Obviously, the further apart the elements are in the periodic table, the better the separation. So if you want to separate lanthanum from lutetium, we can do that really well with this material. If you want to separate something that's adjacent, samarium from europium, for example, it's less good, but that's a very challenging separation and certainly not a solved problem by any means. But the key thing to remember about this data is in the flow experiment, we're essentially looking at kinetics of binding in some sense, whereas in the ITC, we're looking at the thermodynamics. And those are obviously related, but not the same thing. All right, so I mentioned that several slides ago that we were interested in extracting rare earth elements from coal mining byproducts. Typically, coal has been mined for the last several decades for power generation. And so when you generate power from coal, you burn it, and then there's a bunch of ash left over, which is coal minus all the carbon materials, basically. And so we thought, well, here we are in Appalachia. Maybe we can call up our local power company and get a sample of this coal ash and see what's in it. And so we did that, and they had questions initially. Who are you? Why do you want our coal ash, etc. But about a week later, a paint can arrived for us from Appalachian Power full of coal ash from one of the power plants. And so we digested that and put it in our ICP-MS and determined that it's mostly iron and aluminum and zinc. But about 1% of it is actually these rare earth elements. And so naturally, we tried extracting them with this resin. But the challenge is, like iron, for example, is something like 10,000 times more concentrated than our elements of greater interest. And so while our resin could capture the rare earth elements out of this solution full of lots of other things, it was still challenging because a large percentage of these other metals were also captured. So at this point, we think that some pre-separation processing would certainly help in this particular application, which has been explored to a great degree industrially as well. So I'll close this metal chelation section kind of with this overview figure. Fundamentally, we're interested in how the polymer structure affects metal chelation. Thinking about how the hydrophobicity, the chain conformation, the ligand identity interacts with the metal, both in solution, specifically in water, thinking about the thermodynamics, leveraging ITC, NMR, other characterization techniques and simulations to try to get at the thermodynamics of this interaction and to learn something about how we can first study and then perhaps control or perturb the water structure. Then all of this data would feed back into the polymer design itself, trying to develop new materials for rare earth element extraction. And so in my last 5 minutes or so, I'll just give a brief overview of some of the other projects that are occurring in this polymer sequestrant space in our group, starting with toxins. So in this project, we're specifically targeting a bacteria called Clostridioides difficile, or C. diff. It's the #1 cause of healthcare-associated diarrhea and is actually an urgent threat to public health. The bacteria itself isn't necessarily the problem. The problem is actually the toxins that the bacteria produces, an enterotoxin and a cytotoxin, cleverly named toxin A and toxin B. Many of us already have C. diff bacteria in our GI tract, but it's kept in check by the normal gut flora that expresses sugars on the cell surface that bind to and capture these toxins before they cause bad side effects. The problem is, a lot of times these C. diff infections occur when you take a course of antibiotics, which sometimes will wipe out all of the good bacteria in your gut. C. diff is challenging to kill. And so as a result, oftentimes it'll survive antibiotic treatment and then over-colonize the GI tract and cause all these problems. So as I mentioned, these toxins adhere to the normal intestinal bacteria, to specific oligosaccharides, and specifically this alpha-gal trisaccharide, which is known to be a receptor for C. diff toxins. So our overarching hypothesis in this project was that perhaps we could synthesize a polymer particle that could pass through the GI tract. And we would decorate this polymer particle with this alpha-gal trisaccharide that would mimic the normal intestinal flora, capturing that toxin and mitigating all of those adverse effects, particularly in scenarios where the C. diff infection was largely the results of antibiotic treatment. So in those cases, it's not necessarily required to eliminate the C. diff infection itself. Really, you just need to mitigate the effects of these toxins while the normal gut bacteria are recolonizing the GI tract. So that's the concept behind the project. So as far as the identity of that specific polymer particle, we have been focusing on a material known as cholesterol. And it largely comes from the days before Lipitor was responsible for controlling cholesterol in general. It acts as a bile acid sequestrant. So the idea was you'd eat grams and grams of this stuff, and it would pass through your GI tract and bind to cholesterol so that you wouldn't absorb quite so much. Perhaps it looks familiar to you from a few slides ago. Coincidence? Not really. It's synthesized from diethylene triamine and epichlorohydrin to make this network. Then our thought was we'd attach some group onto it, onto which we could couple these sugars, these trisaccharides. So I show this slide, not because I'm planning to go through this synthesis, but rather to emphasize how arduous it is to do glycochemistry a lot of the time. So I always show Brady's picture, who is the grad student in my lab who worked through this, as a thank you to him for taking on this ridiculous synthesis in the lab of a new professor. So Brady cranked through the synthesis. I think it took him about 18 months. And we came out with about 50 milligrams of our final product. So our thought was we have this azide group on the trisaccharide. We would functionalize cholesterol with these alkynes. We do azide alkyne chemistry to click them on. And then when we started looking at their toxicity, we noticed that the cholesterol was non-toxic, putting the alkyne on it was non-toxic. Then as soon as we started doing click chemistry, suddenly became toxic. And that kind of makes sense when you realize that cholesterol is full of amines, and amines are great chelators of copper. And so what we think is happening is that the copper from our azide alkyne click chemistry is getting chelated by the resin. And so many, many washes with EDTA later, we managed to undo that toxicity and get most of the copper out. But in the process, we pretty much consumed our 50 milligrams of alpha-gal appended to these resins. So back to square one synthetically. Not wanting to go through that again, we thought perhaps there's an alternative chemistry we can leverage to attach sugars to these resins. And so we switched over to thiolene chemistry. It's often quite easy to attach thiols to various sugars. We didn't want to test it on the full trisaccharide again, so we did initial experiments just with the lactose. And it turns out that these produce non-toxic resins, which is very promising. So our plan for resynthesizing that trisaccharide is actually to leverage a new NSF center here at Virginia Tech, GlycoMIP, which has some of the only automated glycan synthesizers on the continent of North America. And so I wanted to bring this up in particular just to advertise that this exists. So if you have a project that could benefit from some fancy oligosaccharide synthesized by a robot, please consider getting in contact with the GlycoMIP Center, because it exists to be a user facility with dedicated scientists to work with you to synthesize different glycomaterials. All right, I'll briefly talk about drugs and viruses now. So this project originated during my postdoc actually at Caltech, and it's part of a broader collaboration with the scientists and clinicians at UCSF and Caltech and Purdue and other institutions. And we're targeting treatments for hepatocellular carcinoma, which is the primary cancer of the liver, third most common cause of cancer mortality worldwide. About 3/4 of cases are not amenable to surgery, however. And so in those cases, chemotherapy is essentially the only option. Traditionally, chemotherapy is introduced IV. It circulates throughout the body, targets both the cancer, but also the healthy tissue and causes those notorious side effects. In the case of liver cancers, though, there's a treatment called transarterial chemoembolization, or TACE. And the idea here is that you can maneuver a catheter up through the femoral artery into the aorta, into the hepatic artery, and ultimately into the tumor vasculature, and then inject the chemo directly into the tumor. And when you do this, about half of the drug stays in the liver and about half of it passes through the tumor and enters the general circulation and causes side effects again. So the concept of this project is, can we develop a material and a device that we could deploy downstream from the tumor to intercept all of that chemotherapy before it reaches the heart and enters the systemic circulation? And so in theory then, if we could develop this chemofilter, we would limit the toxicity of the chemotherapy just to the liver or just to the tumor. So in thinking about this project, we're thinking about it along 2 dimensions. First, there's the device material, where all the mechanical properties are going to come from. Is it strong enough? Is it flexible? Can you collapse it down into a catheter and deploy it and then retract it? And then the drug capture material itself. And we and other groups on this project have explored a number of different materials, focusing largely on DNA, on the logic that many of these chemotherapy drugs are DNA targeting. So we can essentially make a decoy target on the surface of these devices, or using ionic groups on our reasoning that many of the drugs have amine groups which can interact with ion exchange materials essentially. But also that cisplatin, for example, is a metal-based chemotherapy agent, and you could potentially start to think about making chelating materials to capture any cisplatin coming out of a tumor. On the device material side, we and others have looked at block copolymer membranes, iron oxide nanoparticles, 3D printed resins. And so I won't cover any of our specific data on this project, but I think conceptually it's interesting to think about and an opportunity for polymer chemistry. Finally, I'll briefly mention our work in antiviral polymers. It's kind of the history in our group. I started in 2017. No one was interested in antiviral polymers. I thought, okay, no rush. In 2018, I got a student who was interested in influenza. And if you had asked me in 2018 what the next global pandemic was going to be, I would have said definitely influenza. Coronavirus would have been my second choice. But obviously things worked out differently. In 2019, we started getting interested in norovirus as well. In 2020, the world became interested in coronaviruses. So in terms of influenza, there are several drugs that have already been developed to try to target different stages in the viral replication. But the key interaction for our purposes is this one between the sialic acid residue on the cell surface and a hemagglutinin protein on the virus surface. And years ago, people realized that if you put a bunch of sialic acid residues on a polymer, you could achieve viral inhibition at much lower concentrations than monomeric sialic acid. And the reason for this is that individual interactions between sialic acid and hemagglutinin on the virus surface are weak, but collectively they're strong because of polyvalency. It's essentially like molecular Velcro. Lots of weak interactions add up to a strong interaction. Once the polymer binds to the virus surface, it's then blocked sterically from interacting with the host cell, and thereby its infectivity is inhibited. So essentially the question of this project is, how do the different polymer parameters affect this polymer virus interaction? And there are many, many parameters that we could think about, and several of these have been explored previously or in the context of different viruses. But critically, each of these parameters will also interact with the other parameters. And so achieving a degree of control over the polymer structure that's really only been enabled in the last several years by advances in synthetic polymer chemistry can we start to unravel some of the complexities of this interaction. Sialic acid also mediates a number of other host pathogen interactions. And so I think it's an open question whether the sialic acid containing materials we develop for influenza might also be applied to many other diseases. Norovirus has a similar story. It's a contagious virus that's commonly called stomach flu, though it's technically not a flu. It affects people of all ages, but it's a particular problem in young people, particularly in developing countries. So essentially, we can ask very similar questions to the influenza project. How do you develop a polymer that interacts with norovirus and blocks its ability to attach to and infect cells? Norovirus, or at least most strains of norovirus, don't bind to sialic acid, but instead bind to histo blood group antigens, which are shown here. And so we can think about developing polymers with these histo blood group antigens on the surface. And those groups also interact with other pathogens as well. Finally, as I'm sure coronavirus needs no introduction, but you may have noticed there's a global pandemic going on, and I suspect that it will catalyze interest in antiviral materials for many years to come, and no doubt dominate the research landscape in this area. And we have a couple of projects working on this as well, which I won't talk about today. But if you're interested in the broader field of antiviral polymers, we do have a perspective article that came out last year that I think gives a pretty good overview of the field, because I think there are opportunities here for polymer chemists in an area that I think has historically been underexplored. And so I think there's lots of room for new and innovative polymers in this field of antiviral materials. And I think now is a particularly important time to be thinking about this area. So with that, since it is the anniversary of me starting at Virginia Tech, I thought I would show the picture of my first day in lab. I don't have a full picture of the group since the beginning of the pandemic, but I like to show the growth of the group in this way because I showed up and got an empty lab space. But the fun of being a professor is really working with the students. They make my job very enjoyable. And so we have a great group of people who have been responsible for all of the work that I've talked about today. I just get to hear about it when they come to my office to tell me about it. So with that, I'd like to thank my students. Ryan Archer in particular was responsible for much of the metal chelation work that I talked about. Brady worked on the CDIF project, Ophelia on chemofilter, Rachel and John on the antiviral materials. Nurin and Connor are also newer students that are joining the metal chelation project, and my other students who are also doing great work, but work that does not fall under the umbrella of polymer sequestrants. And of course, I would like to thank the variety of agencies that have helped us pay the bills over the last few years. And with that, I'm grateful for your attention, and I'd be happy to answer any questions.
Great talk, great talk. Thank you for that, Dr. Schultz. So we are running a little bit behind on time, but we do have a question in the chat. So it's about the metal chelation project. And have you considered enabling some sort of reversible cross-linking with your polymers? And then they're hypothesizing that it could allow for chelation, cross-linking, and then precipitation of the polymer and metal. And then the rare earths could be released upon reversal of the cross-linking.
We have thought about that and related ideas. So a few points. At certain concentrations, you can get ionic cross-linking through the metal to the different chelators. So oftentimes the coordination number of the rare earth elements is 8 or 9. And so it takes several chelating groups in order to fully fill the coordination sphere. So that enables the possibility of interchain cross-linking via the metal. And so one approach could potentially be essentially precipitating out these polymer metal complexes via that ionic cross-linking. I think there's a lot of opportunity in leveraging a lot of the stimuli responsive polymer literature in this area. So you could think about having a polymer with chelating groups, and then introducing some other stimuli responsive repeat unit, something where you could change the solubility based on temperature or light, ideas like this, because there have been so many. There's been so much great work in stimuli responsive materials that I think a lot of it could be imported into this field to great effect. And it's something we're thinking about, but I think there's so much to do that more people should be thinking about it. Did I answer all the parts of that question?
I think you did.
Oh, good. I have a tendency to forget what the question was by the time I'm done talking.
Okay, perfect. So we have gone just a little bit over time, but I did want to thank you again, Dr. Schultz, very much for your presentation, and you too, Dr. McNeil. If we could all give another round of applause for them, that'd be excellent. So that concludes our talk for today, and hopefully we will see you all next Thursday for our next summer seminar series. So thank you all again for joining today.